今天我们非常高兴能邀请到倪教授跟我们做关于英国什么 Causal Graphical Model 和它在Gene Regulation Network 的应用。那么倪教授你本科毕业复旦对吧？是吧？我好记，因为你这个白人没有名就写。
是。
然后你是 Rice 的 PhD 是吧？统计系。
对。
然后在 Anderson Cancer Center 做的博士号，然后在奥斯汀做了博士号，对吧？UT 奥斯汀是吧？
我在 UT 做了博士号，没有在 MD 上。我那个
你在 UT 做了博士号，UT 奥斯汀
老板在 MD
上。那个安德森跟跟 Rice 共同
对
一个 program PhD program OK。然后现在然后就很可惜，原来我们系里面我是主张把他这个介绍给我们系的教授，但是招一个人系里面其实意见是比较复杂的，就是这个事情没弄成，我始终一直是很遗憾。后来这个倪教授现在在调入农工大学统计系这个当教授。他他是后面他也讲的详细，他是两个中心的靠顶那个的，一个是 data science， 一个是统计生物信息。那么他主要做正像他讲的，他主要做我第二了解都是在 causal 方面的，是吧？然后他把这 causal influence 应用到其他的生物学和其他各个方面。他最近也好像跟张看联合主办的一个conference 的 causal influence 的是吧？就是说他在这方面是一个冉冉升起的新星这方面做得很好。所以我们今天非常的幸运能邀请到他给我们做一个讲座。倪教授，我现在那得欢迎你给我们做 talk。
多谢熊老师邀请跟那个非常慷慨介绍。那我今天这个讲座我就用英文讲，但是后面如果大家有问题要讨论的时候，可以再切换成中文。All right, so I'm going to talk about some recent work of mine in the area of causal graphic models for discovering gene regulation. All right, so what is gene regulation? Well, gene regulation really just a causal relation between genes, or in other words, how genes communicate with each other, how they talk to each other, so to speak. So scientists or biologists like to summarize gene regulation using something called gene regulatory network or pathways. So on the bottom left corner of this slide, you see a classic textbook pathway that involves several important genes in cancer, for example, p53. And one of the reasons that biologists or scientists in general are so interested in this type of pathway is because they typically underlie important cellular functions such as cell growth, division, differentiation, death, and so on and so forth. And the disruption or mutation of those pathways often leads to genetic diseases such as cancer. So how traditionally biologists establish such pathway? Well, usually a two-step procedure. In the first step, they have to come up with causal hypothesis, and then typically involving just a pair of genes, let's say AKT and MDM2 in this pathway. And then they will do experiment to verify this hypothesis by, for example, knocking out one of the two genes and see what happens to the other gene. So as an example, let's look at this pair, AKT and MDM2 in this pathway. This paper on the top right corner actually very nicely laid out the exact thought process behind the procedure they coming up with this particular hypothesis involving AKT and MDM2. So in the paper they wrote, we knew p53 regulates cell death. Right? That's something we know. That's something they knew before they wrote their paper or they established their causation. They also said that they knew p53 and MDM2 form a feedback loop. So again, that's also something they knew before they even carried out their study. They also knew AKT suppresses cell death. And then based on these three prior biological information, they come up with this hypothesis that AKT may act on MDM2, or in other words, AKT may be the cause of MDM2 in order to regulate P53. So that's the hypothesis they come up with in that paper, and then subsequently validate this hypothesis. And the way they generate this causal hypothesis to begin with is based on these three pieces of information that they knew. So this way of generating causal hypothesis obviously requires a lot of biological information, biological knowledge. So in this case, we need these three pieces of information to, so that they can come up with this hypothesis. And second, it also somewhat subjective because there are other possible causalities between this set of genes can also explain these three set of facts. For example, maybe AKT act on P53 directly. So that would also explain these three facts. So this way of generating hypothesis, even based on the prior knowledge, is somewhat subjective. One can come up with many different hypotheses that can also explain the same set of facts. And lastly, this way of looking one pair of genes at a time is not a very scalable approach because, as we know, we have tens of thousands of genes in human genome. If you just hypothesize one pair of genes at a time, it's going to take forever to look at all the possible pairs of genes. So, with these three sort of limitations in mind for the limitation of the traditional way of generating hypothesis. So would it be nice if we can somehow automate this hypothesis generation procedure based on observational data alone, which are plenty thanks to next generation sequencing technology. So nowadays we have many observational study and many observational genomic data on the public domain. What if I tell you indeed with appropriate design causal discovery algorithm, which is the focus of today's talk, one can indeed arrive at the pathway or this pathway within a reasonable margin of error without using much prior biological knowledge at all. So I'm not trying to say that prior biological knowledge is not useful. I'm also not trying to say we can get rid of validation experiments. But what I am saying is, with appropriate design causal discovery algorithm, we can potentially significantly expedite this scientific discovery process by coming up with more focused hypotheses in a data-driven way. So this may sound too good to be true because after all, we only have observational data. How can you arrive at something that is causal, right? So to be able to do that, we have to make causal assumptions. So that's inevitable with observational data. Some of assumptions may even hard to verify in practice. For example, no unmeasured confounder assumptions. We will have to be, transparent about this assumption that go into any causal discovery algorithm, so that practitioners, whoever is going to use the algorithm, know your assumption clearly, so they can make their own judgment call as to whether this particular algorithm is suitable for their application or not. So that's the setup of today's talk. So we're going to talk about causal gene regulation or causal graphic model. That's the tool we're going to use, causal graphic model, which was pioneered by computer scientist Yuda Pro and a few philosophers, Peter Sperdes, Clark Geimer, and Richard Shames. So just on the high level, causal graphic model has two components: a causal graph, which basically depicts the causal relationship between a set of random variables. And then the second component is a probability distribution, which tells you how to generate an observation data set. So for example, with this graph, only 3 nodes, we're going to generate x1, x3 first from its marginal distribution because they don't have any cause. And now we're going to generate x2 given its derived cause as x1, x3 from its conditional distribution. Therefore, I can write down the joint distribution as a product of marginal of x1, x3 times conditional of x2 given x1, x3. Okay. So given a causal graphic model, we will be able to generate the observational data from that system. But causal graphic model does more than just generating observational data. And it also tells you what's going to happen if I intervene on the system. Right? So for example, given this causal diagram, if I intervene on X2, then X2 no longer listens to X1, X3 anymore, right? So X2 will take whatever value I set it takes, whatever value I set it to take. So therefore, in general, whenever you intervene on a random variable in causal diagram, it will generally alter the distribution. In this case, the distribution of X1, X3, conditioned on the fact that X2 has been manipulated. Right. So UDPros invented this so-called do calculus framework that allows you to exactly calculate what's going to be the implied distribution after you do the intervention. So I'm not going to get into the details of do calculus for this talk, but it suffices to say that interventions and observations are in general different. Right? So for example, just to illustrate this point, a classic example is, let's say X1 is some sprinkler, so either on and off during the day. X3 is the weather, was raining or not during the day. And then X2 is their common effect, which is the status of the state of the grass around the sprinkler, whether the grass is wet or not. Right? So obviously, if you turn on if you turn on a sprinkler, or if it was raining, then your grass will become wet. So there's so X2 is the effect of X1, X3. And suppose sprinkler is the system that controls the sprinkler is independent of the weather. Right? Suppose that's the case. So in this case, if I observe the grass, at the end of the day, the grass was wet, then knowing that sprinkler wasn't turned on during the day, obviously increases the probability it has been raining during the day, because one of the two causes has to explain the fact that the grass was wet at the end of the day. Right, so condition on X2, it looks like X1, X3 becomes dependent, although marginally they should appear to be independent of each other by design. But on the other hand, if I, instead of observing the grass to be wet, what if I intervene on the grass, do some intervention on the grass? For example, by pouring a bucket of water on the grass, then probably it's obvious that X1, X3 will remain independent given that the grass is wet due to intervention. Right? So therefore, these two distributions are very different. The distribution under observation and distribution under intervention, they are generally not equal to each other. All right? But for this talk, we're going to focus on the first case where we only have data, observational data, that are thought to be generated from a causal graphical model. Okay. So trying to basically go backwards. So given a causal graphical model, we know how to generate data. Now the question is the other way around. So I have data that thought to be generated from some causal graph. The question we ask, or the problem we try to solve is there any way you can back up or reverse engineer the causal graph that is thought to be generated, is thought to generate the observational data you observe? So this is not an entirely hopeless task, because even just based on observational data, we can do hypothesis tests, and we can do independent tests to identify a set of dependence and independence relationships. And for this particular graph, we know that implies at least 3 dependence-independence relationships, as shown on this part of the slides. So now the question is, if I have observational data, if the sample size is large enough, I can test for those relationships. After I get those relationships, can I reverse engineer the causal graph that actually generates this data? So that's the central question we're trying to sort of answer using causal graphic models. So on the next slide, I'm going to use this particular example. So I suppose this is my true causal graph. I generate some observational data, and that joint distribution corresponding to that causal graph implies these 3 set of dependence relationships. And for large enough sample size, just based on observational data, I should be able to infer these 3 dependence relationships. And then let's see whether it's possible to find this causal graph as the true data generating causal graph. Right? So that's, I'm going to show one example on the next slide. So just to remember, these are the 3 dependence relationships we're going to use on the next slide. So actually, the example, the illustrated example, was taken from one of the talk given by Frederick Aberhoff from Caltech. I found the example to be very, very convincing. That's why I sort of stole from his slide. So anyway, we're looking at three variables, which are 3 nodes. And right off the bat, we're going to assume that the causal graph is acyclic. So meaning that you cannot return to the same variable by following the arrows. Okay, so that's not allowed. So if we're making this assumption, then there's only 25 possible causal graph for 3 variables. Okay, so they're listed in this table. So if you recall, one of the 3 independence relation on the last slide was x1, x3. They are marginally independent of each other. Okay, so that's again something you can just test for with observational data alone, right? So there's no intervention required. So then we're going to make the second assumptions, which is called causal faithfulness, which basically in plain English means if 2 random variables, they are causally related, then they should be dependent in the data. So there should be some degree of dependencies or some degrees of association between the 2 because one is the cause of the other. Okay, so if you focus on the graph with the orange background, x1, x3, they are directly causal related. So in some graph, x1 is the cause. In other graph, x1 is the effect of x3. So anyway, they are causally related, but the independence relation on the top left corner says x1 is independent of x3. Therefore, this set of graph cannot be the data generating causal graph. So we can safely eliminate them based on this independence relationship and these 2 causal assumptions. And the second relationship on the last slide was x1 and x2, they are marginally dependent of each other. Okay? So we're going to make additional 2 additional assumptions called causal Markoviness and causal sufficiency, no confounder assumption. So causal Markoviness is basically the reverse of faithfulness, which basically says if 2 variables, they are not causally related in any, directly or indirectly, if they're not causally related, then they should remain independent in the data set. So that's true if you, especially if you assuming there's no unmeasured confounders, then the causal Markoviness basically says, well, they should remain independent. So in this 3 graph with, again, orange background, you see that x1 is sort of isolated from 2 and 3. So they are not causally related at all. So therefore, x1, x2, they should remain independent in your data. But the second relationship on the top left corner, x1 is dependent on x2. So therefore, these 3 graphs are not plausible data generating causal graph either. So we can remove them as well. And just by symmetry, we know once we know x2 and 3 are dependent, we can remove these 2 graphs for exactly the same reason. Okay. And these 2 graphs, for example, they are, well, x1, x3 in this case are not directly causally related, but they are indirectly causally related through the mediator x2. Therefore, x1, x3 should still be dependent. But again, based on the first relationship, x1, x3 are marginally independent. Therefore, we can remove these 2 graphs as well. And the last one, we look at this graph where x1, x3, again, not causally related, not directly causally related, but they share a common cause, x2. Right? Because they share a common cause, they should be dependent as well. Again, a classic example to sort of see that is the graph is somewhat outdated, but it illustrates the points. So on the x-axis, the chocolate consumption per capita for different countries. On the y-axis is the Nobel Prize per 10 million populations. So there's clearly a positive correlation between the 2, but you probably agree that these 2 variables, they are not causally related. So the reason or one explanation why there's a strong positive correlation is because they share a common cause. Maybe the common cause is perhaps, how rich the country is, the GDP, for example, GDP per capita. So anyway, so this assumption, this example basically illustrates the point that whenever 2 variables share a common cause, they will appear correlated or dependent in the data. But again, x1, x3, according to our observational data, they are marginally independent. Therefore, this graph cannot be the data generating graph either. We can safely remove it as well. And just based on this full assumption and these three dependence-independence relationship, again, we can easily test for based on observational data alone. We end up with just one unique causal graph. That's actually the true data generating causal graph we started with. So you may wonder, well, there must be a catch. Yes, there is a catch with this procedure. In addition to having to make those full assumptions that on the top right corner, this procedure that I just introduced may not always eliminate all but one causal graph. So in other words, in more general case, you may end up in something called equivalent class. In fact, we can partition this 25 graph into several Markov equivalent classes. Within each class, all the causal graphs, they may look very differently. They have very different causal interpretations, but unfortunately, they have exactly the same set of dependence-independence relationships. Therefore, obviously, based on the procedure that I described on the last slide, you cannot tell apart graphs that are falling into the same equivalent class. So the implication of that observation is that, say if this graph, the bottom left corner, the graph on the bottom left corner in the yellow equivalent class is a true data generating graph, then based on the procedure I just introduced in the last slide, all you can see is one of the 6 graphs is a true data generating graph, which is clearly unsatisfactory for many applications. So ideally, we want to always be able to tell which one is the unique causal graph that generates the data. Sometimes you get lucky. So for example, in our example on the last slide, this graph, the equivalent class it belongs to is a singleton equivalent class. Therefore, with just conditional or dependence-independence, you can uniquely identify the true causal graph given a large enough sample size and with those causal assumptions. But in general, especially for a large network with multiple nodes, equivalent classes tends to be very, very large. Right? So therefore, the focus of this talk is to introduce a few methods that do allow you to always reduce your equivalent class size to 1. Okay, so that, in other words, you can uniquely identify the causal graph no matter which equivalent class it belongs to. Okay, so that's the goal of this talk. So we're going to talk about, depending on the time, we'll be able to, I plan to go over 2 or 3 methods we developed in the last 3 or 4 years. And let's start from the first one. We call it direct acyclic graph, or DAG, for discrete ohmic data. So it is specifically motivated by ohmic data that are discrete. But as you will see, it's more generally applicable to other data sets as well. All right, so just a little bit on the sort of history or literature review in terms for the causal discovery with discrete data. So causal discovery or causal graphic model for continuous data has been very well studied in the last 30 years or so. Okay, so a lot of work come up every year. But for some reason, the progress for discrete data, which is the focus of this part of the talk, is very limited. So before we published our paper last year, the general belief at that time was identifying those equivalent classes that I showed a couple of slides ago is the best anyone can hope for, except for a very few peculiar cases. So for example, if you're willing to assume that the discrete variable or discrete data somehow follows the additive noise model, which is hard to imagine or hard to, at least in my opinion, hard to understand. So they basically, this set of papers prove that under those peculiar cases, yes, you can narrow down to one causal graph. But other than that, generally, you can only identify equivalent classes. But there's an important piece of information that had mysteriously always been overlooked in the literature for some reason, which I still don't exactly know, is that discrete data are often ordinal. That includes the motivating data, motivating ohmic data that tends to be ordinal discrete data. For example, a common practice in bioinformatics, when they're dealing with gene expression data, they will discretize the data into, say, 3 categories: overexpression, normal expression, and underexpression. So this is obviously ordinal, right? So there's an inherent order in those 3 categories. But beyond those discretized data, there are some data sets that are just naturally ordinal. For example, survey questionnaire. So if you ever respond to questionnaire, let's say if the people who conduct the survey use the Likert scale, say 5 point, then you typically answer a question using strongly disagree, neutral, agree, strongly agree to certain statement, right? And obviously these 5 categories are ordinal as well. So there are a lot of discrete data or categorical data that are ordinal by nature. So why not using this ordinal information, taking into account this ordinal information when building your causal graph? So for whatever reason, nobody has ever looked at this ordinal information in the causal discovery literature, which I found very, very surprising. So the main contribution of this work is to establish or to convince people that one should not discard ordinal information for categorical data if they are ordinal, right? So ordinal information is in fact absolutely crucial in causal discovery for discrete data. So before we get into the details of the model and the theory and the real data, I would want to emphasize here that when we do classification, maybe your class label may be nominal, maybe ordinal. You can get away with just applying a nominal model for ordinal classification tasks if your sample size is large enough, because after all, for classifications, all you care is prediction. So ordinal data is more parsimonious than a nominal model because it involves fewer parameters than a nominal classification model. So maybe in small sample, ordinal model can perform better than a nominal model for ordinal classification tasks, just because model complexity is smaller. But you probably don't care if your sample size is large enough. They probably behave more or less the same. But here the scenario is very, very different. For an ordinal data, if you use nominal causal discovery algorithm, then no matter how large your sample size is, you will never be able to identify a unique causal graph. But on the other hand, if you're using ordinal information, taking into account all ordinal information in building a model with a finite sample, you may be able to identify the causal graph. And certainly in the infinite limit, you will be able to identify the true causal graph. So that's very different from the distinction between an ordinal and nominal classification. Here, ordinal information is absolutely crucial for discovering causality. So anyway, I'll get into details right away. So the model we consider is extremely simple, almost embarrassingly simple. So we have a set of random variable xj, denoted by xj. J runs from 1 to q, and we require that the number of level or the number of categories each variable has to be at least 3. Okay, so binary variable won't work. So we have to have at least 3 categories. And then we have seen this formula, a simplified version of this formula a few slides ago when we talk about this example, right? So, but this is just a more general version of it. Basically says, if I have a causal graph G, then I can write down the joint distribution of X, which contains Q random variable, is a product of conditional distribution, where each conditional distribution is a distribution of a variable, xj, given its direct causes. Right? So a fact given its direct causes. So we have seen the simplified version of this a few slides ago, where this is a more general formulation. All right, so then this is nothing new. This is just this basically a definition of causal graphic model or Bayesian network. Sometimes it's also known as Bayesian network. So with this formulation, there's actually only one thing left us for we have to decide, which is the right hand side, the conditional distribution on the right hand side of this equation. Right? So what is the model we're going to put on xj given its direct causes? Well, xj are we assume it's ordinal, therefore a natural choice for this conditional distribution is just a ordinal regression model, okay, or ordinal classification model. So we choose to use the cumulative conditional probability distributions as a representation of the ordinal regression. So it's really just a vanilla ordinal regression, nothing really new here. So this f is some link function. So you can pick whatever your favorite link function is, say logit or probit or whatever you like. Yeah, so any link function basically. Beta is the regression coefficient, alpha is the intercept, and gamma is the ordinal regression category specific cutoff. So nothing really new here, standard ordinal regression, right? So that's it, that's our model. Our model are basically two very standard components. One is the DAG factorization that everyone knows in the causal graph literature. And second, for the conditional distribution in the DAG factorization, because we're dealing with ordinal data, we use ordinal regression. So the model is extremely simple. But the essential questions that we're going to ask, we're going to try to answer in this talk, in this part of the talk, is this model does more than the equivalent class that we can identify with nominal model, nominal causal graphical model? The answer is yes. We can prove that if you're willing to make no unmeasured confounder assumptions. So if we are making this acyclic no unmeasured confounder assumptions, then we can prove ordinal DAG, the model that we just proposed on the last slide, is uniquely identifiable, meaning that we can always identify a unique causal graph. So we don't have to worry about equivalent classes anymore. So I'm not going to show the proof for this talk, but instead I'm just giving you some intuition as to why this may be even possible, right? So we're going to look at a simple example, just involving two variables, x and y. Right? So we'll start from the model that x, in which x causes y, right? So in the blue model, x causes y. So as I mentioned earlier in the talk, that a causal graphic model tells you how to generate observational data, right? So given this causal graph, I'm going to generate x because it doesn't have a cause. So I'm going to generate x from its marginal distribution, right? So say, for example, this is the marginal probability table. And then conditional x is the cause of y. I'm going to generate a fact variable y, conditional on its cause, based on this conditional probability table y given x. Okay, so these are just a few numbers that I come up with. Okay, so these two tables, of course, leads to the joint distribution. Right, so you multiply the conditional by the marginal, you get a joint probability table. Right, so that's simple. But of course, nothing stops you from factorizing this joint distribution the other way around. I can always get the margin of y, conditional of x given y, right? So that's factorization of probability. And that, of course, corresponding to the reverse, or something called anti-causal model, the reverse direction, right? Because now I'm going to generate y from its marginal, so y is not going to have any cause. And then I'm going to generate x given y, so x becomes the effect of y becomes the cause of x. So that's another way to see that why these two causal graphs are in general not identifiable from each other, because they both imply the same joint distribution. So that's why if you imagine that you generate data from either model, and you fit two models to the same data set, no intervention, just observational data, they will have the exact same likelihood function. So therefore, there's no way you can tell apart these two causal graphs. And in fact, they are Markov equivalent in this case. They belong to the same Markov equivalent class. Namely, there's no independence relationship between these two variables. They're dependent on each other. But what I haven't told you about this particular example is, if you focus on the first graph, x causes y, the blue model, the numbers you see in this table, in these two tables, y given x and the margin of x table, those numbers are calculated based on this particular choice of parameter in the ordinal causal graphical model that I introduced 2 slides ago. Okay, so these numbers are calculated based on this set of parameters. On the other hand, this red model, the reverse direction, if you consider y1, y2, y equal to 1, 2, 3 as ordinal data, and use our ordinal causal graphic model, you cannot find any particular value or combination of values of gamma and beta such that the implied probability of x given y and y match those numbers. You cannot. You cannot find any set of parameters that will lead to exactly these two distributions. You simply cannot. So the difference here is, without considering the ordering or the ordinal nature of y and x, they're equivalent. The red model, the blue model, they're equivalent. Therefore, you cannot tell them apart, even with infinite sample size. But once you consider or take into account for those ordinal nature of x and y, and actually only one model is consistent with the ordinal causal graphic model. Therefore, they give you an intuition as to why this may be identifiable. And the theory we have, of course, is proved that this is generally true, not just for this set of parameters, right? This is a very specific choice of parameters, but our theory basically proved that this is generally true. So whatever parameter you choose, there's actually only one direction is consistent, or there's only one direction that actually equivalent to this joint distribution, right? So indeed, if you can actually verify by a very simple simulation. So in fact, if I generate data from this joint probability table, right, I actually generate 100,000, which is pretty large sample size for this two-dimensional problem. And you try to fit this red model to this data set. Even with this large sample size, you still have a substantial bias compared to the truth. You can imagine that if I use the blue model, it can get arbitrarily close to the true values. And with this wrong model, even n goes to infinity, you will always have some bias. The bias will not diminish as n goes to infinity. Right? So that sort of hopefully illustrates why, on the intuition level, why the causal model may be identifiable once you account for the ordinal nature of the data. Well, the theory is proven under relatively strong assumption. Particularly, we have to make an assumption that there's no unmeasured confounders. So even if you don't care about theory, let's look at empirical evidence. We have a lot of simulations, but I'm not going to show any for the talk because, as you know, they always work. Yeah. So we're going to just look at real data and see how this type of algorithm works in real data. Can we really identify causality based on observational data without intervention whatsoever? So we have a few data sets that we use in the paper, but here I'm just going to tell you about two of them. So if you're interested, you can check out the paper and see more validation, real data validation. So anyway, the first real data we consider is a very well-known data set called SAC single-cell flow cytometry data. It's a protein data, measures 11 phosphorylated proteins in 853 human T cells. Okay, so Q equal to 11, and the sample size is 853. The raw measurements of the protein expression are very skewed and noisy. And for that reason, the original author who published the paper in Science 2005, they actually provide data that are discretized into 3 levels: low, average, and high expression. So obviously, these are ordinal data. One of the reasons that this data is actually very popular in causal discovery literature or community is that in their paper, they also provide something called consensus causal network of those proteins accepted by the scientific community at that time in 2005, by 2005. We acknowledge that it's not perfect knowledge, right? In biology, there's no real ground truth, but for our purpose, we use it as a ground truth anyway for evaluation purpose, so that we can apply different methods on the same data set and compute error against this consensus network, so we can compare different methods, right? So although it's not perfect, we use it as a ground truth anyway. So in the original paper, they would just use something called a nominal categorical DAG model. Like I said before our paper, for some reason, people would just discard ordinal nature, the ordinal information in ordinal data, and treat them as nominal data. So they actually, the method they applied is exactly a nominal categorical data, DAG model. And with that model and with just observational data, they can only recover very, very few edges and have false discovery. So let's look at how our method performs. The graph you see on this slide is the consensus network they provide in the paper. Okay, so we're going to use this as ground truth. And of course, when we apply our method, we pretend that we don't know the ground truth. So we're just going to throw in the protein expression data and let the algorithm figure out how to wire those different proteins. And this is our result. All right. First of all, we have a lot of false negatives. So all the black lines are the lines or the causal relationship that we miss entirely. Okay, so we have 12 of them. But we do have a few true positives. So we have 6 true positives. We are represented by the blue arrows. So those are, we identify the link correctly. Also, we identify the direction correctly. Right? Both are correct. The presence of the edge is correct, and the direction of the error is also correct. So we call this true positive. And then we have two orange arrows, and they are well, we identified the link successfully, but our orientation from the algorithm is reverse of the consensus orientation, right? So even though we do have 12 false negative, so in other words, the method is not that sensitive, but I would say the specificity of our method is very good in the following sense. First, it didn't add any spurious link at all. So there's no additional link we add. So that's very, very specific. Second, among the link we identify, which is blue and orange, 8 of them, out of these 8 links we identify, 6 of them are in correct direction. Okay, so in those two senses, our method is very specific. And for these two orange arrows, which are reversed, there are a few explanations. It could be just false positive, but also, at the consensus network was given in 2006. So it's a network that is accepted by authors or researchers at that time. But there are some more recent study and shows that actually this direction also makes sense. In fact, there are also some evidence in more recent literature suggests that there may be feedback loops between these two pair of proteins. So therefore, after all, these two reverse edges may not be wrong in the end, but we don't know for sure. Lastly, I also want to emphasize that for this type of algorithm, causal discovery algorithm, in my view, in my opinion, specificity is more important than sensitivity, because one way of I envision people using this type of algorithm is to use for hypothesis generation, right? So after you generate the hypothesis, the subsequent steps involving validation experiments. So the biologists have to spend time and money to validate this hypothesis. So a false positive will lead to money wasted and time wasted. And on the long run, it will undermine biologists or research scientists' interest in this type of algorithm. So I would rather an algorithm to be more specific than more sensitive. Anyway, that's one algorithm. That's one data set we look at, and we apply 14 or 15 different algorithms, state-of-the-art algorithms on the same data set, and then we look at the errors or structure Hamming distance. Lower is better. I show the top 8 of them, and in this particular data set, we are the best across all 15 methods. All right, and we also have other data sets. For example, this data set called cause effect pair CEP benchmark data set. It actually contains 99 data sets across 37 domains. So beyond biology, so we have economy, engineering, meteorology, and so on and so forth. So there are many different domains that this data set are collected from. Each data set contains a pair of variables x and y, for which the cause and effect relationship is clear from the context. For example, x may be the age, y may be a glucose. So obviously they are correlated, and probably the age is the cause of the glucose, not the other way around. Right? The glucose does not cause you to age. So that's true for all the pairs in these 99 data sets. So we know, again, in other words, we know the true causal relationships, and we pretend we don't know when we fit our model, and then we compare our estimation versus the so-called truth. Okay. So here's the result. Again, we compare to many methods, but we just show a few relevant methods here. So OCD is our methods. Out of this 99 pair, we were able to identify 73%, so significantly higher than 50%. So if you have to guess, that will be a 50% causal discovery method. So we are significantly better than a random guess. We are not the best in this particular data set. We're second best. The best method is slope. BQCD is also pretty good, 72%. HCR is not that great, but it's very, very similar to, it is the most similar method to ours. That's why I listed here. So overall, OCD is still the proposed method is still very, very favorable, has very favorable performance compared to state-of-the-art in this data set as well. As I mentioned, I actually have some other data set in the paper that also sort of support the utility of our proposed method. So if you're interested, please check the paper. We have more examples there. And then we also have some extension of this current work. For example, we extended to nominal data. So it turns out there's something we can exploit even with nominal data using a similar idea as ordinal DAG. And second, we also created a few more benchmark data sets so that other research can benchmark their methods against. And in fact, we create a benchmark data set from out of mass and data sets in R using the same principle. So we're going to look at pairs of variable, and we're trying to see whether this pair variable has very obvious causal directions. And when they do, we put this in our benchmark data set. Okay, so we manually look at all the possible pairs in these two R packages, and we have put the data sets in this package COLP. So if you're interested, you can check out this data set in this COLP package. And we make two R packages, implement these two methods: the ordinal categorical discovery, ordinal causal discovery algorithm, as well as the nominal categorical data causal discovery algorithm. So they are both available on CRAN and GitHub. So if you're interested, feel free to check out. Okay, so I think I will skip this part just because of time. In a similar approach or in a similar way, we develop a few other methods that dealing with different features of data. So in this particular case, we are motivated by single cell data, which is known to be, first as a count and very highly skilled, and it's zero inflated. So there are a few features that a lot of sort of off-the-shelf causal discovery methods do not take into account. So we show that if we take into account those features, the power of we can identify more causal relationships based on observational single cell data. So they are published in various venues, and some are still under review. But for the interest of time, I'm going to skip this part. But it's the same idea. We have some identifiability theory, and we also have real data validation, and it shows that our method is significantly better than other methods, as well as random guess for single cell data. All right, so for the last maybe 10 minutes or so, I'm going to talk about a complete different work that allow us to relax three assumptions that we have to make typically. One is we typically make assumption that the graph is acyclic. But as you know, in biology at least, and I'm pretty sure in other many applications as well, there may be feedback loops. So this acyclic assumption is not appropriate for those applications. So we're going to relax this assumption in this part of the talk. Second, in the previous two parts, the theory always assumes there's no unmeasured confounders, which of course almost impossible to check in practice. So we're also going to relax this assumption in this part of the talk. Third, typically people would assume data are generated from some IID distribution. But in this motivated example where we have cancer genomic data, the IID assumption typically does not hold. So we're going to relax this IID assumption as well. So we're going to relax these three assumptions in this part of the talk. All right, so the project actually started a few years ago with a actually very different goal. So at that time, it was more like a modeling problem. We're trying to model, genetic association networks, and we're trying to make this network capable of capturing some dynamics as a function, of disease states, disease progression. And we thought this would be useful to model tumor heterogeneity because different cancer patients may have very different genetics, architecture, and so on. That includes inter-tumor heterogeneity, intra-tumor heterogeneity. So ideally, at that time, we want our gene regulated network can change over the course of cancer development, and so on and so forth. So anyway, that was the original, goal or motivation of this project. But it turns out this heterogeneity or cancer heterogeneity is actually very useful for the purpose of discovering causality. While most existing causal discovery methods, which typically assume at least partially IID observations, which can lead to misleading results if your data is not IID or not partially IID. Our methods will explicitly account for heterogeneity, data heterogeneity, and in fact, it is precisely the heterogeneity that allows us to identify causality. So we're going to show that even in the case where there's cycles and there's no unmeasured confounders. Okay, so for this part of the talk, we're going to use something more general, a model that is more general than the DAG factorization you saw earlier in this talk. So we're going to use something called structural equation model. And this model will degenerate to DAG model if we make certain assumptions. But without those assumptions, it will be more general than DAG. So anyway, for simplicity, we're going to assume in this work, we're going to assume the data is continuous, leave on the RQ space. And we're going to use a structural equation model, which is given by this equation. One thing to notice is this x variable, this x vector appears on both sides of this equation. That's the key. Okay. And for that reason, we can model cycles. So anyway, so this B matrix is the key quantity of interest. So it's Q by Q. And the only assumption we make is the diagonal is 0. All right. So the interpretation of any elements in this B matrix is, say, BJK is the direct causal effect of K to J. Okay. So by setting BJJ equal to 0, we're excluding self-loop. So we do not allow a node that regulates itself, because otherwise it's going to be non-identifiable. But since we're not making any other assumption on this B matrix, we allow cycles. For example, if BJK and BKJ, they are not equal to 0 simultaneously, then there's a cycle between J and K. So we allow that in this model. And like I said, this structural equation model would degenerate to DAG factorization that we saw earlier in this talk if we make the following two assumptions. One, if we make the assumption that the graph is acyclic, or in other words, if B matrix is lower triangular after row column permutation. All right, so that's equivalent to acyclic assumption. And second, if we make the no unmeasured confounders, or equivalent if we assume this covariance of the errors is correlated or is not diagonal, then if we make the diagonal assumption, then the assumption no confounder is made. Under this two assumption, this structural equation model will degenerate to DAG. Okay, but in this case, in this part of the talk, we're not going to make either assumption. So it's going to be cyclic. It's going to have possibly unmeasured confounders or correlated errors, in other words. All right. So anyway, this model has been studied for many years. It's not new at all. So it's not something we propose. But there's some limitation to this model. I'm just going to highlight two, but there are actually other limitations as well. First of all, related to what I said about heterogeneity. So when people use this structural equation model, SEM, they typically assume the data you observe from this SEM, generated from this SEM, are IID, independent identically distributed. Okay. Or in other words, they assume this E sub I, this error, is IID from some normal distribution. Okay. That's a typical assumption when people use SEM. But as I said, this may not be a good assumption for cancer data, because the cancer patients, their genetic distribution is probably quite different from patient to patient. And second, perhaps more importantly for this talk, is we know it's not identifiable. The causal graph behind this structural equation model is not identifiable even in the simple case, where we assume that it's acyclic, there's no unmeasured confounder. Even we make it this too strong assumption, this structural equation model is still not identifiable. It's only identifiable up to Markov equivalent class. So these are the main two limitations of the SEM on this slide. So we're going to modify this SEM with a, well, again, very, very simple model. Yeah. So we're going to introduce something called a latent variable, Z sub I. So notice that this latent variable is indexed by the observation. So we assume this Z sub I is taking real value. And in our particular example, in our particular application, this Z sub I can be interpreted as latent disease progression, as we will see in a few minutes. But notice that this Z sub I can be just some latent variable, which doesn't even have to have any physical meaning or interpretation. Okay, this is just a way that we can use to model the heterogeneity of the data. All right. Particularly, I'm going to insert this latent variable Z sub I into the parameter A and B. But most important is the B. So forget about A, it's not that important. So we're going to model this B as a function of Z sub I. So Z sub I is latent. And we're going to write this B matrix as a matrix function of Z sub I. All right. And because Z sub I now is indexed by I, therefore, actually the distribution of Xi is not going to be identical anymore across I. Because actually that distribution depends on B depends on Z sub I. So therefore, that's the way we sort of account for the heterogeneity in the data set. So in terms of interpretation, this BJKZI is basically a patient-specific causal effect, right? So if we're dealing with patient population. And the ZJK Z sub I is not equal to 0 if K cause J for patient I. So obviously, with these formulations, for two different patients, their BJK may be different. Maybe one is 0, the other is not 0. Therefore, the causal structure actually can change from patient to patient. And importantly, once again, we do not assume B to be lower triangular or sigma to be diagonal. I think I'm running out of time. We show that it is identifiable even without cyclic consumption, without acyclic and no unmeasured confounder assumptions. Again, we're not going to show the proof, but instead we're going to just look at one real data set and see how powerful this method is compared to existing methods. So this data set is a pretty old data set, a public data set from TCGA, breast cancer gene expression data. So we have over 1,000 heterogeneous tissue samples. Out of this 1,200 samples, we have 113 normal tissues, and the rest is tumor tissue. So that we know. We know exactly which tissue is normal, which tissue is tumor. So that's something we know. We're going to focus on genes from a few important pathways. Part of the reason is the method is not very scalable yet. It's a Bayesian method, but also we know these genes are very important for breast cancer. Okay, so we're going to focus on this set of genes. And even though we do know the tissue states, right? We know some of the normal, some of tumor. When we fit our model, we pretend we don't know. Okay, so we kind of use this information as sort of a validation. All right, so there are two results I want to show you that generated from our methods. The first one is the latent variable estimation. Okay, so on this scatter plot, we have the first two PCs, principal components of the gene expression data. The color represents the ZI, the latent factors, the latent variables. Okay, the actual value doesn't really matter. What matters is whenever two dots they have similar colors, that means the corresponding latent variables are similar to each other. So that's all we care. And I overlay using this sort of marker shape, using star to denote normal tissue and dots to denote tumor tissue. Again, this information was not used during the model fitting stage. Okay. So what we sort of surprised us is, basically all the stars have this red and the yellow color, meaning that they are sharing or they have very similar latent variables. With a few exceptions that there's a few stars are blues, but the vast majority of the stars the vast majority of the stars have either red or yellow color, meaning that they are very, very close in the latent space. So that gives us some confidence that at least in this particular application, this Z sub I kind of indicates the state of the tissues. So that's the result from latent variable estimation. But what we're more interested in this case is causal discovery, right? So let's see the causal estimation. So this is the example that I used to motivate this talk at the first slide. Right? So these are I call it textbook pathway. So that's something that has been well established in the biological community. Okay, so that's our estimating one. So we of course make some errors. So we have one false negative denoted by this dashed arrows. So we did not identify this link, which should be there. And we have two false positives, which are represented by this dotted arrow. Again, I think we have a reasonable power and a pretty good specificity. So notice that we identified this cycle correctly. We did add two false negatives, but overall, we did not add many false positives. So we're pretty happy with this result, at least for this pathway. But of course, this is just a small pathway. We also tested our algorithm on different pathways. Okay, so in fact we tested on 8 different pathways, and again we compared to many alternative state-of-art algorithms that also allows you to do. Some of them also do cyclic graph. So there's one pathway that we lost to LIN, the linear non-Gaussian cyclic graph model, but then for the rest of 7, we're either the best or there are few are equally good. Okay, so overall, the black bar, which indicates our methods, are very good. So by the way, the measure MCC is a measure of errors, and the higher is better. And so from this plot, it looks like our method performs very well compared to the state of arts for this data set. So with that, sorry, I think I'm already out of time. I would like to make some acknowledgements. First of all, I really like to thank 2 of my students who actually carry out the work, especially the second and third work. And also acknowledge, I'd like to thank Bani Malik, who I collaborate with on the first project, and Kejing from IUC, co-advising student founding, and also Robert Checking, who actually who is a biologist who provide our single cell data for us to play with. And lastly, I also like to thank my funding agency, NSF and NIH, to support our work. And with that, these are some of the selected references that we mentioned. So if you're interested, feel free to check them out. And then I'd like to take any question if you have any. Thank you very much.
我们呢再一次非常感谢倪教授给我们做的精彩报告。现在我们现在还有9半小时时间提问，希望大家踊跃呢提出你们自己的问题。
倪教授非常精彩的那个报告，我想问一下，就是因为这个谈到这个 scalability 的问题，就现在大概这个 causal 这个 graph， 你现在这个 node 比较就是 manageable 是可以最多可以做到多少个？
最多可以做到100个左右吧。
100个左右 ，OK。然后这个 edge 呢 ，edge 数目的话，这个
edge 的话，理论上跟那个 computation scalability 没有什么关系，但是呢，
没有关系，
但是跟 power 有关，对吧？就是你的 graph 如果很 dense 的话，是需要更大的 sample size。
对，就是你现在 typical 的就是说，如果这个 edge 是还是比较假设比较 sparse 的是吧？
对，一般来说，比如说是如果是 p 个 node 的话，一般假如说它的 edge 也是在 p 个 order。I
see.
Big OP， 比如说。
I see.
我看那个 chat 里面有2个问题。你第一个是这是数学是概率图模型对面。对，这个是属于那个 probabilistic graphic model。然后 probabilistic graphic model 一般来这好几种 graph， 最常见的是2种，无向的图 underived graph 和有向的图。然后这里因为你要做 causal 的话，就必须得用有向的图，所以我主要是做有向的图。还有第2个问题是 why discrete data is more challenging for causal discovery？ 这是个好问题我猜是就是为什么就是从一个角度讲啊，就是为什么有那么多 continuous 的 model 发表在 conference 里，为什么 discrete 特别少？一个原因可能是，这当然是我猜的，一个原因是因为可能 continuous model 你有很多 model 的 assumption 可以 make， 比如说你可以 assume 你的 data 是 Gaussian 或者 non-Gaussian， 你可以 assume 你的causal mechanism 是 additive 还是 non-additive， 你可以 assume 你的即使是 additive， 你可以假设它是 non-linear 还是 linear。 It turns out 这些不同假设都可以 lead to causal identifiability。 对于 discrete data 对于离散的数据可能这些假设比较难。比如说如果是 categorical data 的话，那你可能不能说我用个 spline， 比如说去假设它的 categorical effects 是 non-linear， 所以这个假设你就没有办法 make。 这是我猜原因之一。还有一个原因可能是，我想一下，还有一个原因就是可能大家 可能跟我之前说的，可能大家认为 categorical data 可能你最多就只能 identify equivalent class。事实上，那个 causal 就是 the DAG 和 Bayesian network 刚出来的时候，大家其实都是做 categorical data，很多人就用 multinomial 或者 categorical distribution 做 Bayesian network， 做的人非常非常多。只是说，可能大家那个时候就觉得啊，可能这个equivalent class 就是能做到最好的，可能这也是一部分原因。
对，我还有一个问题就是你在后面的部分讲到的是你那个用 structural equation model 去那个去 relax 这个 assumption， 那其他的方法当中大家是怎么去 relax cyclic 的这个 assumption 呢？大家是大概有些什么样的approach 去 relax 这个东西呢？
对于 cross-sectional data， 这是我唯一知道的。但是如果你有 time series data、time course data 或者 longitudinal data，那就要容易很多。比如说，如果你是 time series 的话，你就最常见的就用那个 VAR（Vector Autoregressive Model）。这样的话，其实就是时间上有 cycle 了，那这个就很正常。对 ，A cause B， 然后 B 又 cause A in the future， 那这样就 cycle 了。但是在 cross-sectional data 下，也许有其他方法，但是这是我知道的唯一的方法。它的 idea 其实就是假设，它也其实有个假设，我没有在这边没有讲，是它假设你的 data 还是假设你有个 dynamic system， 比如说是一个 differential equation system， 是 AR model， 但是呢，我只是有个 snapshot， 但我假设这个 snapshot 是这个 data 是 collected 的时候，它已经进入那个 equilibrium， 已经在 stationary distribution 上。
就是早期的那个 burn 的那个阶段。
对，就必须得make 这个假设。如果你愿意做这个假设的话，这个 structural equation model 就可以用来 detect cycle。
对，那大多数可能应该 data 还是符合这个的，因为很多还是 steady state measure， 就是那种大规模的 gene expression 这种。
对，事实上这个 structural equation model 你可以 prove 在一些的 assumption 下，一些 condition 下，那个我刚刚说那个 AR1 model， 你让它 goes to infinity， 它收敛的那个 station distribution 就可以用这个 structural equation model 给表示。或者换句话说 structural equation model 就是它的stationary distribution。
对，还有一个我比较不太清楚，就是你的这个 pathway 的 inference 那几个 regulation， 你最后还是只是从 RNA-seq 你就得到这个 relationship 是吧？没有去用其他的 modality 去看过。
对，没有。
所以这个还蛮 surprising， 因为很多调控不是在 RNA 水平的，所以这个还蛮有意思的，就是其实你从 RNA 水平就能够得到大多数的这个 regulation 的关系。
是，所以当然如果有其他的 modality， 那当然更好。如果能做 data integration， 可能信息更多一点。
所以理论上，你如果是看 transcription factor 跟这个调控关系，你应该是成功率更高一点，说不定就是从你这个。
对，其实我刚刚那个 skip 的那个 work 就在做这个，就是我们找了一些 transcription factor 跟它的 target， 找到这个 database 里面的一共大概479对。然后我们用了这个 method， 然后可以 identify 304对。对，这个时候在这个 work 我们确实用了这个 transcription factor 当然我们是用来作为那个 validation 了。假设我是已知这个 transcription factor， 知道这个 target， 然后看他们能不能找到这个方向是对的。
所以你说从如果有不同类型的数据的话，现在领域里面大家用什么方式去把它整合到你这个 structure equation 里面？还是如果是不同类型的数据的话？
有，我之前做过一个 work 就是说 OK， 如果 X 是比如说是 gene expression， 然后比如说我有个 Y 吧，Y 是比如说SNPs 或者是 DNA level 的，或者是 methylation epigenetics。那有一种方法就是我 incorporate prior information， 就比如说我知道 DNA 会影响 RNA， 但不会反过来，那我就相当于是把 Y 值放在这个等式的右边。比如说我固定了这个方向，从 Y 到 X， 然后 X 不允许回到 Y， 这是
就是你固定一个 directional 固定一下。
对，这个 direction 固定，然后你可以证明就是说你一旦把这个 direction 固定了以后，这个对你 identify B 是有利的。
对，
有点类似于 instrumental variable 的概念。
对，所以 causal inference，因为我看到经常有一些 GWAS 的还有用到一点，像这种类型的用，就是所以比较好奇这个
对他们那个做 GWAS 做那种 Mendelian
randomization， 对，
他就用 SNPs 作为你的 instrument base。对，我们最近也在做一个，就在做用 protein 跟 SNPs，想知道 protein 跟 protein 之间的 interaction。I
see。
SNPs 做 instrument。
还有其他同学、朋友、教授有什么问题吧？我的两个问题哈，第一个问题哈，反正是像你这个离散的哈数据对不对？能不能够把它转为某种程度上成为连数的？比如说哈，在这个skewness equation吧，这个模型对吧？这个这个加性不是个加性，这个性对不对？它年来哈在做这个，因为skewness equation模型嘛，大部分它变量是连数，但它结构呢，它以前呢都是用组合化的方法来求，是吧？离散组合化，所以它当时的那个规模吧，得能做到100个，那就讲的就是用那整数规划这个做啊，就是我们曾经有个学生对吧？他们做也是做到100个左右变量对吧？但是呢，你如果把它就是说变成连数的最优化，就把这个要素塞个那个对不对？这个要素条件呢，你想办法把它列出来。他们这个性呢，他们呢在2018年呢发表一篇这篇文章，这个大大的加速了这个他们的求解，能够呢规模嘛也扩大。所以现在呢，因为那当然它只包括那个内在变量，没有包括外在变量。如果是我们就是说内在变量、外在变量都包括做的话哈，那现在呢，我们可以把这规模扩大到1000个nodes，这规模嘛就扩大了很多。那你现在呢离散的这个办法对不对？我看到哈麻烦的问题哈，就是说你哪怕就是做两个 pairwise 的，它都有一个问题。假如说你要用到那我们在数学上来讲比较方便的办法嘛，实际上是梯度化，数解最优化呀，它就是可以求导数的。如果说你有办法把这个问题对不对转化为矛盾形式的哈连数，这个能够用导数来求，那这个速度大大提高，有没有可能？我问一个问题就是，
对，我知道那个连续那个 diagonal tiers 那种通过连续作为优化的方法去快速求解，然后我现在能想到的一种办法就是通过 latent variable， 对吧？如果你是 ordinal 的话，你可能可以 impute 一个 latent 的 Gaussian， 然后并且加上它的 cutoff， 因为你任何一个 ordinal data 你都可以 impute 一个 either latent Gaussian 或者 latent logistic 去做，也许然后在 logistic， 然后在这个 latent level 上放这个 structure equation model， 也许可以用那个diagonal tiers 那 framework 去做梯度的优化。但我不知道有没有在我 to the best of my knowledge， 我不知道应该是没有这样的 work， 应该是没有人做过这个事情。当然这个东西我不知道，因为你在 Bayesian framework 上你就 sample 这些 latent variable 就完了。我不知道在一个那个梯度的优化的算法里面怎么去做这个事情，可能可以做 EM， 但是这个得还有需要一些思考。当然，我们最近在做这个 scalability 的问题，我们是在用那个 variational inference 在做，就相当于是抛弃了这个 full posterior， 然后用 variational inference， 或者甚至更简单的是直接做梯度的，也不叫梯度吧，叫 coordinate ascent。然后，其实我们后来发现，那个 coordinate ascent 其实可以比那个 diagonal tiers 还要快好多了，对。我们之前好像考虑了几千个 node， 当然不是这个复杂的 model， 最简单的 model， linear Gaussian 的 model， 我们考虑了几千个 node， 然后 用那个 coordinate ascent 非常非常快，那个到几千个 node 的时候，那个 diagonal tiers 就是either runtime error 还是就是跑了2天没跑完，所以那个其实我们发现还有一些其他算法也可以把这个加速，就不一定是一定要梯度算法。
你比如说哈，现在因为关于这个它这个离散的哈，如果呢我们讲派外是 causal 对吧？你刚才讲的 x 到 y，y 到 x 对吧？这个方向对吧？其实呢，不要是速度不速度，它的这个如果说没有特殊处理啊，就是说它的 causal 的这种本身的就正确性啊，我们讲到 true 对不对？它实际上都有某些困难。就是说我们原来的一种想法在做的时候啊，它就是说这个就是我们已经是用生成式地空网络，啊，就是 GAN 吧，就是来看它的那个离散的变动的 causal， 就是它一个方向可以哈，第二个反方向过来做呀，因为他们这个做这个 causal inference 不是要这是两方面嘛 ，x causal y，y causal x 要样，对不对？就是说这个你在每个最好的decision，但反方向来很难。所以最近呢，就是说我们在试什么呢？就是说你加上一个 diffusion model，diffusion process， 把它的那个生成式地空网络呢改造，就是这个呢，看就是反方向的问题哈，就可能比较容易解决。就是说，因为离散性的数据的数据哈，图理啊。确实，因为你已经很几个例子来说明，对不对？那么它的分布吧，它不是我们的连数分布，就是不能用正态分布啊之类的，对不对？一定要离散分布，所以这种离散分布吧，你应该在你的模型里面确实像你讲的，应该保留。现在问题就是说，把这个离散性的分布的东西，对不对？你怎么在一定程度上连续化，才能加速它的一个进程？就是说这个问题。第二个对不对？就是在基因表达这个数据里面哈，你吧，假设真正的做基因表达，因为基因这里讲究几万个基因对吧？几千几万，那我自己体会，你比如说 drug discovery 对吧？你 drug target 它的团体变化呢是一个假设讲一个基因到另外一个基因到另外一个基因，不管这中间的过程是 mediation 呢还是不是 mediation， 就是这个 mediation， 那你想的怎想的弄出这样一个途径，在一个过程出来。那么你有没有比较啊？就是说你用离散我看到你写的例子吧，你是用离散化做的，对不对？跟连数做的啊，就是说他们就是准确率 accuracy， 就是说像你把一个连数变量有个人分3段，对不对？这个就分。那另外呢，然后呢，你用离散化的这个因果分析，就是你的模型去做。但或者我们直接用连数的去做，就用连数的 skewness equation 结构方程来做。这个 accuracy 你有没有比较？
有，比如说这个 sex 这个 data， 这个它本身是连续的嘛，但是因为它是 highly skewed 跟 noisy 的，所以它那个原来作者他其实提供2个版本，他原来连续的版本加上他那个 discretized 的版本都有。然后我们的方法当然是基于它那个离散化以后的数据，但是比如说这个方法 BQCD， 它就是基于连续的。然后这其实大部分都是基于连续，除了这个 HCR 是基于离散的。其实大部分我们比较的方法都是连续的。然后至少在这个 dataset 上，似乎这个离散化以后反而效果更好，这个 structure handedness 更小。我的感觉是这样的，就是离散化当然有好有坏啊。好处就是你不用在意它原来 distribution 是什么。我们那个方法是 agnostic to 它原来 distribution。那坏处当然你也会损失一部分的 information， 对吧？因为你毕竟扔掉了它本来的 raw 的 measurement， 而只是把它归为3类，低、中、高，对不对？但是但是你直接用连续的模型去处理连续数据也有它的问题，就是它一般也需要 make distribution assumption。 那当然你这个数据实际的数据里面符不符合这个 distribution assumption？ 它要是符合，我相信它的 performance 肯定会非常好。但如果它不符合，那当然它也就会performance 就没有那么好。所以我觉得综合来看，其实在 real data 里面很难说哪个到底更好，要看你的，其实看你本质上就是看你的 assumption。对于连续的模型，就是你看你的 assumption distribution assumption 到底符不符合你的数据。对于离散模型，我觉得可能如果对，我觉得如果数据量够大，然后你用的就是你这个 category 足够大，当然我这里只用了3个 category， 但是如果你因为数据不够大嘛，我们这边只有800多个样本量，所以3个 category 可能也就极限了。你再多的话，每个 category 里面的数据太少了。但如果你数据如果足够大，然后你用多一点的 category， 那我觉得可能你损失的信息也不会那么大。那在这个情况下，我觉得可能离散的模型就优势就会大一点，因为这样我不需要 model 我不需要知道任何关于原来那个 raw measurement 的 distribution， 我不需要做任何假设。
好的。大家还有什么问题吧？跟大家什么不理解的，或者你有什么建议，有些什么疑问？这个是我们这个论坛的 causal inference 的第一次报告，第一次报告。原来呢，我们后面呢还要做一系列的报告，因为这个咱们这个论坛呢，其中呢有一部分内容是讲 causal 的这个，因为现在吧，因为在人工智能里面有最近发展很快，生成式人工智能很多内容，所以呢 causal 呢inference 呢就是往后走，后做。因为这里面实际上有很多问题，对吧？我讲这个，我随便我们讲一个问题，对吧？我养个图 ，graphics 你怎么来叫来 causal， 对不对？我在微博流行上怎么来做？就这些问题，对吧？因为我们微博流行论坛吧，这是当时我想到的这些事情，就属于呢这个以后吧，就说这个显然吧 ，causal inference 吧。它也是人工智能中的一个很重要的部分。即使智能语言呢，你仔细去想一想，假如说，对吧？智能语言中间，你普通的 listening 跟 causal 它们之间的意图有什么相同之处，有什么不同之处，对吧？就这些东西，就是这个呢，就是我们今天呢，我非常高兴就是说，倪教授呢，给我们做了第一次做了 causal inference 的竞赛报告，开拓我们的思路，对吧？我们再一次感谢倪教授给我们做了竞赛报告。我们今天的这个论坛呢就到此结束。谢谢。
谢谢熊老师的邀请呀。好，拜拜。
那好的，那谢谢，晚安。
晚安，拜拜。
拜拜。